Yeah, here we go, recording. Okay, so here's what we were talking about last time. We were talking about surface integrals, and the big idea is just like with line integrals. It's that we have a domain that we still want to do a chop it up, add it up, whole is the sum of the parts argument, but the shape of the domain, the nature of the domain is such that, well, it just doesn't really fit in any of our previous forms, right? So we define a new Riemann sum with a new notation and a new terminology to go along with this idea that we're going to take our surface and, as we do with really all of the types of domains we see in this class, we're going to chop it up into little pieces. We're going to make arguments on each little piece. And then we're going to add up over all of the pieces, right? So basically the same idea of every other integral we've ever talked about. So we talked about how to compute this with a pullback. This time, instead of pulling back through a change of variables function, we're pulling back through a parameterization. It's still a pullback, and there's still a corresponding notion of a stretching factor, which again is something that we can that we've already argued, and we don't need to re-argue. Okay. All right, and then various examples. So where we're going to pick up now is how do we apply these ideas to different kinds of accumulating quantities on surfaces. And the one in particular I want to talk about is flux. So y'all will recall flux. Flux is this formula right here. Right? And the purpose of this formula is, well, there's actually kind of two purposes. It depends on what the nature of your vector field is. If your vector field is indicating velocity of the fluid, then flux computes volume per unit time of fluid passing through your surface. Okay, and that's nice and all, but what if, as is sometimes natural and important, what if your vector field represents density times velocity? Well, in that case, flux, same formula, mind you, right? But because we're making different assumptions about the vector field, it's now computing quantity per unit time going through your surface. Point being, though, for various different reasons and various different circumstances, flux is an interesting quantity. All right, now we've got this formula. Bad news. This assumes certain things that are not always true. For example, it assumes that your vector field is constant, right? That it's exactly the same vector field everywhere on your surface. That's not always true. What if the vector field was like this? Now my vector field is not constant. And this formula does not apply. It doesn't even make any sense if you think about it. It also assumes that our surface here is flat. Right? And, well, sometimes our surface is flat, but very often it's not. So again, we need to generalize our formula to get around the fact that sometimes our vector field's not constant and sometimes our surface is not flat. In fact, usually neither of these is the case. Okay. All right. So we are going to make a whole is the sum of the parts argument. Now you'll see here in the notes that there's various discussions here about orientation and unit normal vectors and stuff, and I'm going to skip past that for the moment. We'll come back and talk about that in a minute. First, let me just talk about the chop it up, add it up aspect of this. If you have a whole surface, it's not flat, right? It's all curved and stuff, and you have a vector field. Let's see here, surface. Yeah, you have a vector field F that is not constant. It's widely varying. It's got different directions, different magnitudes, whatever. It's just varying, right, all over the surface. What are we going to do? How are we going to deal with this? We're going to make our usual argument. That is, we're going to chop up our surface into little pieces. We're going to look at each little piece at a time. On each little piece, well, the whole point is that it's a little piece. Stands to reason that little piece would be approaching flat. Not exactly, right? It's a little bit curved, but close enough. Certainly in the limit it's going to approach flat. And the vector field, again, because the piece is itty-bitty and little, right? Again, let's not worry about regularity issues, but you would expect as the piece gets smaller and smaller, the vector field just wouldn't vary very much, right? Because there's just not enough room for it to change. And so its vector field should be approximately constant. So on the little pieces, we can use our old formula. On the little pieces, then, we write down just, let's see, I guess I'll zoom out a notch. We write down this. So the amount of flux through the one little piece of surface, F dot n times the area, and of course the area of this little piece is ds. How we doing? Everybody on board? Quick reminder, just for sort of visual aid purposes, this little piece here, I'm expanding here to see it bigger and better, and so the vector field approximately constant over the entire surface, and this little piece of area approximately flat. Okay. All right, and then let's go ahead and do the added up portion. This computes flux. This right here, color choices, computes flux on just this one little piece. That's a little differential piece of flux. If I want to add that up over the entire surface, right, then I have to integrate. I have to say, well, okay, let's add up over all little pieces. This gives us then our what we're going to call a surface integral, right? Just sort of recopying like so. And it's tempting to say, okay, well, cool, this is just a surface integral. We've written down stuff that looks like this before. We've got an integral, and ds is our integrand, and from that point of view, it's all familiar. But there's a twist. There's a complication here. And this, I want to point out, is highly analogous to the situation that we found ourselves in back in Chapter 6. Recall in Chapter 6 we were talking about line integrals. And when we had a curve like this, you chop it up into little pieces. On each little piece, like this, on that little piece, you can make a simple argument and say on that little piece, okay, well, f is approximately constant, and the piece is approximately flat, and f dot dx, computing work and all of that, and then you just kind of plug that in. But we had to recognize here that what we have as a result, this integral that we get as a result is fundamentally different. And this is a really different thing. For one thing, it matters which direction we're going. So, for example, I have to say what is the direction that we're moving along that curve. Said differently, it has to be an oriented curve because the direction matters. Right? And so that's why we had to come back down here and look at this thing and confess that, you know what, this is actually a pretty different construction. We called it a vector line integral as opposed to scalar line integral in recognition that the orientation matters. And you'll even see specifically, going a little further down in this page, that this notation for a vector line integral, even though you see the ds scalar, right, it remains that the t vector matters, right? That t vector is part of the integrand, and that's not supposed to be the case for a scalar line integral. So it's kind of, depending on how you look at it, sort of two reasons or two different sides of the same reason that this is a fundamentally different kind of a thing, and thus vector line integral. So same story over here. Looking at a piece of surface, if I want to talk about how much flux there is through that little piece, which direction are you talking about? Right? It's really not obvious. You could mean that this is the positive direction through the surface, in which case we would mean that what I have here, is my normal vector for use in that calculation, right? It could be, right? Maybe. But also perfectly reasonable. Just as good of a question. Just as natural. Maybe we want to consider this other direction through the surface. Right? There's nothing magic about up as being just automatically correct. So maybe we mean this green vector down here as our normal vector. Maybe that's what we want to consider the positive direction through the surface. So we have an orientation issue. So again, just like with vector line integrals, vector surface integrals take place over oriented surfaces. You can't just say surface, right? There has to be an understanding of which direction is the positive direction through the surface. What, in other words, is the orientation of the surface. Okay, so, yeah, and here we are down at the bottom then. Again, you have to pick which direction, and then furthermore, notice that orientation becomes part of your integrand. This is not a scalar line integral where you have a scalar integrand. A scalar differential and a orientation independent integrand. It's just not true, right? The orientation matters, and there it is, right there. Just like with vector line integrals. Okay, so following the previous notational pattern, I'm going to group these two things, both of which are telling me about things having to do with the surface. This telling me how big is my little piece of surface. This telling me the orientation of my little piece of surface. All of that together, we're going to call the ds vector. And it's just a notational thing. It's analogous to recall in a development of vector line integrals when you find yourself looking at integral over a curve of f dot t ds. Analogously, there's the orientation vector telling you how your little piece of curve or surface is oriented. There's the size differential, length in this case, area in that case, size differential telling you how big your little piece of domain is, and then the product, let's see here, the product of those telling you everything you might want to know about that little piece of curve, just like with this little piece of surface that previously we called it, pencil, sorry, hang on, pencil. Previously referred to that as the dx vector, and thus the analogy, we call that the dx vector, and likewise we're going to call this the ds vector. Is everybody on board? Everybody see the analogy there? Comparison? Okay. All right, so it's just notation. You're welcome to use whichever notation you prefer between these. I will point out this notation has the advantage it's more compact. There's fewer pen strokes, right? A little bit more efficient to write down. And also, I feel just a little bit more elegant, again, in the sense that this ds vector is kind of an all-encompassing thing telling you about the domain, and thus leaving the integrand completely independent of the domain, like every other integral we've ever written down. Okay, so vector surface integral is the term. Again, vector because the differential is a vector, and the integrand also a vector. Okay, good news, we already know how to compute these. We have all of the necessary tools already in place from previous work. So in particular, don't forget we have this idea of a parameterization of a surface. Right? We have these previous calculations that we've done. Right? And all I got to do is to kind of write down what I need in this particular case. Here's the development that we wrote on the previous page. That's just all recopied. And let's see here, our ds, as discussed in the previous section, our ds is magnitude of capital N times ds dt. And let's see here. Now notice I can group these together. And now, full disclosure, I'm about to commit a little math crime. I'm going to confess to the crime later, but I am going to commit the crime for two reasons. First of all, I don't want to get bogged down in details where there's enough going on already. We will come back and deal with this issue later. But also, I like to dramatically illustrate just how easy it is to make this mistake. Right? So this isn't easy to make mistakes that I want you all to be on the lookout for. So anyway, now proceeding with my little math crime. Let's think about this product. It points in the direction perpendicular to the surface, just like capital N. It has magnitude equal to the magnitude of capital N, just like capital N. This product here, little n times the magnitude of capital N, looks like a duck and quacks like a duck. And so I argue that it's a duck. It is capital N. Now again, it points in the same direction as capital N. It has the same magnitude as capital N. Doesn't that make it capital N? So the argument goes. And again, I'm making this for dramatic purposes. I did just commit a little math crime. We are going to come back and clean that up in a minute. But for the moment, let's just run with it. And what's nice about this, and by the way, it's not all wrong. Okay. So anyway, let's do a calculation with this. We're going to compute a flux with this formula right here. Notice that this formula is entirely pulled back. Everything is a function of S and T. It's just a matter of plugging in. And here we go with an example. Let's compute here. Let's see here. We're going to compute the flux of this vector field arbitrarily through this surface. You see, oriented upward. Okay, so we have an oriented surface. In particular, it's part of a certain graph, specifically the part of that graph that's sitting above the unit square in the XY plane. All right, so we have a vector field, we have a surface. Let's compute the flux. We know capital N is going to be necessary. We know that capital N comes from the parameterization. So, as one would expect, the very first thing I'm going to do is parameterize. This being a graph, I'm going to use the graph parameterization. Now, that's a callback to some ideas that we talked about last time, if I remember correctly, last time or the time before, recently certainly, how to use the graph parameterization to parameterize a surface. Make sure you're good with that. It's an important technique we're going to be using a lot. So with your parameterization, now we take the appropriate partials, just a little bit of calculus, no big deal. We take the appropriate cross product. That gives me my normal vector. And at this point, then, I can just say, okay, well, there's my normal vector. Come to think of it, here's my vector field. That's already given. Plug and chug. Okay. Specifically, there's the vector field. Now, there's a little tweak subtlety here. You'll notice that what I've got written down there for the vector field doesn't look exactly the same. Don't forget you have to plug in. You have to pull back through the parameterization. So, in particular, notice it says right here z squared. But don't forget what z is. Z is the third coordinate of the parameterization. So where it says z, you've got to plug in what z is. Right? And likewise, where you see x, you've got to plug in what x is. X is s. And likewise, let's see here. So y, what is y? Well, according to the parameterization, come on. Y is t. Is everybody good? Yep.
How do you know that capital N is pointing upwards?
Yeah. That's the dirty little secret that I've swept under the rug that I'm going to come to in just a couple of minutes. Yeah. Now, you caught me. Good job. Right? You busted. Right? We'll get to that momentarily. Yeah. So this is the plug and chug mechanics, and of course, then this can be computed. Just crank it on out. It's an integral in the ST plane, and easy to do. How I'll segue per your question. How did I incorporate the fact that this is oriented upward? And in this case, it actually is oriented upward. This is a sloppy use of the word upward. Upward you might take to mean exactly, perfectly straight up, right? But when you're talking about orientations, language is allowed a certain amount of flexibility because otherwise there's no word to describe exactly what direction this points, right? And so in particular, what makes this upward is the fact that if you look at the third coordinate, that third coordinate is positive, which means, this capital N vector could be pointing something like this. That's not exactly perfectly straight up, but it's not downward. There's no sense in which this is downward. Right? So upward is if we had two vectors to choose from, like this, that are negatives of each other, this is the only one of those that could possibly be considered upward. The other one is if anything, downward. This one is the one that's upward. Does that make sense to everybody? Yeah.
So we just kind of got lucky that cross product happened to be positive?
Yep, got lucky.
Okay.
Yeah, no, that's right. No, I totally agree that you very unsatisfied look on your face is right, and there is a better treatment that I'm going to show you now. Okay, so here's the lead-in to my confession of my math crime. There's actually two different unit normal vectors in play, and I deliberately conflated two different things for dramatic purposes. So let's talk about what those two different things are. We were given a surface. Well, let me just say, in general, you'll be given a surface. Keep in mind, if you're asked to compute a flux, you need to be given an oriented surface. It has to say in the statement of the question, this surface oriented this way or that way, and how to talk about orientations. We're going to say a few words about that in a few minutes, but for the moment, let me gloss over that. So, in particular, being as it has to be an oriented surface, we need an indication of which of the two possible orientation unit normals are we talking about. Are we talking about, as I have it drawn here, the upward-ish one or the downward-ish one? These are two different oriented surfaces. They're not the same surface. And the question has to say. Okay. Now, just to have an example to talk through, let's suppose that we're talking about, and to make it stand out on the page better, let me use the darker green. Let's suppose that we pick the dark green here as our given orientation for our surface. Fine, we're given a surface. We want to use the formula we just made. We therefore have to parameterize. And of course, the parameterization does a lot of stuff. The parameterization allows you to compute your XS and your XT, the cross product of which allows you to compute your capital N vector, which is pointing in the direction of a normal vector. Right? This is what we're going to call the parametrized unit normal. In fact, we've previously discussed the parametrized normal vector. This is just the unit vector pointing in that direction. So, now you see by the example that I have illustrated here, it is not given, and in fact, half the time it is not true to think that the orientation unit normal and the parametrized unit normal would point in the same direction. They're completely disconnected from each other. The orientation unit normal is given. It could go either way. It's arbitrary in some sense, but it's given in the statement of the question. The parametrized unit normal comes from the parametrization that you made up yourself, personally, right, that coin flip might just as likely as not be pointing in the opposite direction as the given parameter, the given orientation unit normal. So this is the issue. Again, 2 unit normal vectors, and there's no reason to think that they should be pointing in the same direction. Is everybody with me? Okay, so this conflation is my crime, and in particular, this is the moment in the algebra. Again, keep in mind, I put this little asterisk here, right, that we're going to come back and talk about this later. Here we are, talking about it now. And when we rewrote the original form of the integral, this thing right here came from the statement of the question. This was the unit normal vector that was given in the statement of the question. This was the thing that I had initially dotted with my vector field for the purpose of computing flux. That is the given orientation unit normal. Then I claim that that's equal or related to this capital N vector, which of course has a direction and a magnitude, and the direction in particular given by the parameterization unit normal. So I claimed inappropriately, mathematically illegally, I claimed that these are the same. Right? I mean, I didn't write it as such. I claimed that these were the same, but effectively I was claiming that these are the same. Effectively, therefore, I was claiming that these are the same, and you can see they're not. They're unrelated, and coin flip, 50-50, they're different. Okay. All right. So there's 2 different ways you could approach how to handle this problem. One is you could say, hey, when I parameterize, make sure to parameterize in such a way that your parameterized orientation is consistent with your given orientation. And if you can do that, cool. Right? If you can ensure that your parameterized normal and your given orientation normal are the same, no problem, proceed. The downside there is I don't know how to do that. It's hard to see it coming when you parameterize, right? Who's thinking as they parameterize in terms of which way is that normal vector going to point? Nobody's thinking in those terms. It's actually pretty hard to think in those terms. So here's what I advise. Just recognize that you might parameterize upside down. If you do parameterize upside down, you're just going to be off by a minus sign. Just identify after the fact whether you parameterize upside down or not, and if you did, throw in an extra minus sign and you're good. And I think this is by far the easiest way to proceed. Yeah, question?
How would you know if you...
Yeah, totally. I'm going to get there next, absolutely. So that's my advice. Good news, by the way, this is the only issue with parameterizations other than this orientation issue. It doesn't matter how you parameterize however you feel like, makes no difference. And again, except for the orientation issue, it is true that the ds vector can be written in terms of the parameterization with this little formula, in du dv, or, depending on what your parameters are, it might be in ds dt or d phi d theta, whatever, right? But that's all fine. Just make sure to recognize that you've got to think about that orientation. Okay, let's see in an example how to actually do this. Here we go. Now, this is a very similar example to what we saw previously. Same vector field, same portion of a graph. The only difference is that here I'm, instead of deliberately arranging it to where we get lucky, like we did here in this example, I arranged it to where our parameterization and our given orientation would be compatible. Now I've arranged it to where we're going to get unlucky instead of lucky. And I'm going to point out here how to identify when you've gotten unlucky and how to fix it when you've gotten unlucky. So here you go. Let's see here. Graph, parameterization, partials, cross product, all that's the same. Nothing changed there. And here's where you have to take a pause. And by the way, this is part of the student's responsibility. I'll call it the person doing the computation. In this case, the student, right? It's the computer's, that's a person, not a machine, the computer's responsibility to know to pause and think about it at this stage once you've gotten to what your capital N vector is. And what you have to do is, again, compare. Look at the given orientation. Look at the relevant part of your parameterized orientation and just ask if these are compatible with each other. Now, what is the relevant part of the capital N vector? It depends on the verbiage being used to describe the orientation, and there's different examples, and we're going to talk some other examples later. But I make the case right now that if you want to decide if your normal vector is pointing upward or downward, you would tell that by looking at the third component, the z component, as to whether it's positive or negative. And what you see here is that we have a mismatch. We have a positive third component in my parameterization normal vector, indicating that this is, if anything, upward. Our orientation, though, says it was supposed to be downward. We accidentally parameterized the wrong way. We parameterized, you might say, upside down. And so our parameterization is to blame. Now, good news, you don't have to start over. You don't have to re-parameterize and hope that you parameterize correctly the next time. Just stick with what you've got, but recognizing that these are opposites. I'm just going to observe that, no, I parameterized the wrong way. I'm going to fix it with a minus sign in recognition that every single term in my integral is exactly backwards, aka my answer is going to be off by exactly a factor of minus 1. I fix it by putting in an extra factor of minus 1, and we go about our business. It's as simple as that. That makes sense to everybody? Okay. All right. So let me finish up these details, and I have a couple other things I'm going to say about this. So let's see here. Yeah, we fixed it with a minus 1. Let's see our vector field. Again, plugging in, pulling back through the parameterization. That's what our vector field looks like. Our capital N vector, we recopy from above. And now we have an integral ds dt. This is just a plain old dot. You got to crank out the dot product. But this integrand is a scalar function of s and t. This is a chapter 5 style double integral. Everybody happy? Okay. Now I'm going to remind y'all of something. I know y'all hear me say this a lot, but it's important. That's why I repeat myself over and over again. So this is a class about ideas, not answers. Right? A lot of people have the mistaken impression from the way things were done in high school courses, or possibly even explicitly stated in some high school courses, that if you're doing a computation, all that matters is the answer at the end with the box around it, and that's the only thing that matters. And if that's right, then your answer is right, and who cares about all the stuff above? Is that was just for your own personal, private purposes. And again, reminder, that is absolutely not the way it works in this class. In this class, we're looking at the whole thing. Right? So here's the thing. You got to make sure that you put this minus sign in the correct spot. Right? So let's suppose, for example, that the proper place for it to go would be, let's say the proper place to put it would be, I'm going to say right here. And let's see here. Let me fill in a minus sign right there. Okay, so let's suppose that this is where the minus sign shows up in the calculation. If you put the minus sign in the wrong place, let's suppose you put the minus sign first here. And then it's tempting to say, well, come on, who cares, right? The point is it still gives rise to the same minus sign at the end. It doesn't affect the answer. Okay, well, it doesn't affect the answer, but again, reminder, the answer isn't what matters. What matters is the reasoning. So let's see what this does to the reasoning. To the reasoning, you've got an equation here saying that that is equal to this, which is not true. Right? And then you also have an equation here saying that's equal to that, which is also not true. Right? So you got two false statements there in your reasoning. Now they happen to cancel each other, but it remains that's two false statements. It's arguably, you might say, two conceptually important sign errors. So it's importantly wrong. Right? So again, the big point here is to make sure you put the minus sign in the wrong place. Remember that when you write down the ds vector, right, or when you write down little n ds scalar, right, any normal vector that comes from the given orientation of the oriented surface is one side of the relationship, and then the thing that comes from the parameterization is the other side. Where you have to put the minus sign is in the transition from the one to the other. When you claim a relationship between the orientation and the parameterization, that's what those are the things that are distinguished by the minus sign. So the minus sign goes at the point where you switch from the one to the other. Does that make sense to everybody? Okay. So, lots of different versions of how to get this wrong. One thing you can't do, you can't just, for example, if you were to put the minus sign, let's see here, am I in the right mode? Yeah, if you were to put the minus sign here, wrong, and wrong, right? And if you were to not put it there yet, but, put it here, well, then wrong and wrong. Right? So think it through carefully. Make sure you put the minus sign in the correct spot. Also, one other thing. Please also don't rewrite, don't replace capital N, as being, so our usual formula for, where did I put the, no. Where's my, anyway, close enough. Right, N is the cross product of your two partials of your parameterization. Don't rewrite and say, well, I'm going to define N to be minus XS cross XT. Because that's wrong also. The capital N is defined as being this cross product, independent of the parameterization. Right? So that's not sort of an up for grabs option. Okay, I hope all that makes sense. Little subtleties. Okay, so moving along, let's talk about terminology. When we talk about orientations, it is a little awkward. Take, for example, this surface here. There's two possible orientations we could have on that kind of cereal bowl, as it were. And those orientations are what you might call, I'm going to just say the green one here. And then what I'm going to call the blue. Blue doesn't stand out very well. Let's say orange. Orange. So we have a green orientation. We have an orange orientation. These are our two candidate orientations. Yeah, is everybody good? Okay, so how would I distinguish these? Is there a perfect word that perfectly describes exactly the direction that all of those green vectors are pointing. No, of course not. How obscure would that word have to be, right? There's so many different surfaces. We can't have a word for every single one, right? So the understanding is that when you describe an orientation, the job of the language is just to unambiguously distinguish between the two options. So for example, if I were to say, let's see here, if I were to say upward, the nice thing about this word upward is that every one of these green vectors that I'm describing is at least somewhat upward. And furthermore, that word upward in no sense describes any of the orange vectors that I'm trying not to refer to. So the word upward, it's not exactly perfectly geometrically accurate, right? Not very few, I guess technically one, but very few of these green vectors are actually pointing straight upward. But the word upward unambiguously picks the green orientation and rejects the orange orientation. Is everybody with me? So that's the goal. That's the goal. Just to distinguish unambiguously between your options. So upward versus downward makes loads of sense here. Now you can kind of sort of also get away with inward versus outward, and you'll notice that I have kind of a little right thing over here. There's a quibble here. If I say inward versus outward, technically there is no inside to this surface, right? I mean, it's, but then again, I mean, if you say the word inward, nobody's picking the orange orientation. I think it's pretty clear. It's just not it's suggestive of a geometric feature that's just not there. There is technically no inside to that surface, so it is a little uncomfortable. But anyway, everybody see what I'm talking about there? Okay. So now you look at this next scenario here. Let's look at this surface, and here inward versus outward makes loads of sense, right? Inward versus outward could not be more clear. Perfectly fine. Okay. Whereas if you say upward here, upward, well, some of the outward vectors are upward, but some are not. Arguably worse, some of the inward vectors are upward also, right? So upward just does not cut the mustard at all. You can't say upward versus downward for this surface here. Is everybody happy? Okay, so be careful with the language. Think through the examples that I've got written here. You're going to see me use orientation language in many subsequent examples, and try to always be thoughtful about the trade-offs and is the language really doing the job that it needs to do? Okay. Sometimes you get lucky. Very often you get lucky. It's really, really worth it to be on the lookout for fortuitous circumstances. So here's one. We have a surface, namely the sphere-oriented surface. That is, it's oriented outward. And then let's see here, we've got this vector field given, and with those two givens, we want to compute the flux. Fine. Now you could parameterize the sphere. Here's the problem with parametrizing the sphere. X, Y, and Z each would be chock full of trig. Each one of these would be chock full of trig. And then you're also going to have to take the various partials and, cross product, and then it's, oh my gosh, that'd be a tremendous amount of inconvenience. So I don't think that's a good plan. Let's hope we can find a better option. And in this case, we get lucky. So the lucky observation to make here is that because this is a sphere, spheres have this wonderful feature, I should say spheres centered at the origin, have this wonderful feature that the position vector and the normal vector are always parallel. They point in the same direction. That's a unique feature of spheres centered at the origin. But it's pretty awesome. And knowing that it is pointing in the same direction, and knowing further that the that the lowercase n, that the unit normal is a unit vector. Not hard to argue exactly the formula then for your outward unit normal. And I can just plug that right on in here. And notice I didn't, missed. I did not even parameterize at all. Right? Just writing down from convenient geometry, just writing down what the orientation unit normal is, and recopying the vector field, I can just straight up compute that dot product. It's 0, game over. Everybody see how awesome that is? Just be on the lookout. You never know when you're going to get lucky like this. I would propose that whenever you have a surface where the geometry actually permits you to just, without parameterizing at all, you can just write down your normal vector, do it. There's a reasonable chance you'll get lucky, and that will lead to super easy, super convenient solution like this. Everybody okay? All right, here's another example. Here we go. So, okay, right. So we have a surface. It's part of a certain plane. Here's the plane, y equals 3. We're looking specifically, S is the part of it that satisfies this weird inequality. Okay, so fine. So S is actually just this dark blue surface right there. It's not a disk. Right? Notice those fourth powers in the inequality. But this is vaguely disk-like. It's anyway, the point is some kind of lumpy surface inside of that plane. Okay. So there's a couple of really nice bits of good fortune here. First of all, notice we've been asked to compute a flux on this surface. This surface being entirely inside of this plane, and that means that everywhere I care about, y is equal to 3. And I can just toss that right into there. Right? Tossing y equals 3 into here makes this term, this whole second term here, or second coordinate, I should say, that whole second coordinate is just 0. So my vector field simplifies really dramatically. Just noticing that the domain tells you some algebraic things, and those algebraic things can combine in nice ways with other algebraic things. Everybody with me? Okay. So that's a big win. A lot simpler thing there. Here's the other big win in this problem. Because we are entirely contained in this plane, this plane being as it is, easy to understand, it's just the plane y equals 3. I can use some chapter 1 skills, and I can immediately write down the unit normal vector. Simple geometry, right? The plane y equals 3. The normal vector is parallel to the y-axis. Notice it says here, oriented in the positive y direction. That's why I know it goes that way and not that way. Everybody good? Okay, another lucky break, and I get to rewrite my normal vector like so. And so I haven't really done any work yet, right? I haven't, taken that deep breath and parameterized and taken partials and cross product and the blah, 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 the whole, spiel, process that we usually go through. Just some clever observations, and I can conveniently observe that my integrand is 0, and we're done here. There we go. So dot product is 0, game over. Flux is 0. Everybody happy? All right, so you'd be surprised how often stuff like this comes up. So please do always be on the lookout. Don't just Every time you see the question said flux, don't just reflexively write down where's my formula? Don't just reflexively write this down and start plugging and chugging. You might, two things. You might, on the one hand, end up giving yourself a lot more work to do, but more importantly, you are missing out on clarity of thought, and keep in mind clarity of thought is part of the grading. If there's an easy way to solve a problem and you do it the arduous way, then that communicates that you didn't understand that particular concept. So very important to keep your head on a swivel and always be on the lookout for good fortune. Okay, here's another notational necessity. For the purposes of this class, I mean, this is mostly liability. This isn't going to help us compute anything, right? But there's stuff that you're going to see out there in the real world when you're looking at work that uses surface integrals. It goes like this. Recall that formula we just talked about. Recall that the normal vector is this cross product, which I can rewrite by coordinates, and which I can just cross, write down the whole cross product one coordinate at a time, and you get this. And we previously observed how weird that the coordinates of capital N look like little 2x2 determinants. Okay. All right, that we previously noted. Where I'm going to go with it now is to point out that if you just take the ds dt and distribute to each of the coordinates, and then you look one coordinate at a time, I mean, what do you think we ought to call this thing right here? And in another context, where we were doing a change of variables from the st plane to the yz plane, we wouldn't give this a second's thought. We would just write that down as dy dz and proceed. Right? Because again, with the now again, this is another little math crime, but it's like those cancel. They don't, right? But it's as if they do, and so very reasonable to call this dy dz. Seem reasonable? Okay. And then likewise, of course, for these other coordinates, that should be dz dx, and that should be dx dy. Now, real quick. A lot of people have an instinct to put things in alphabetical order. Got to resist that instinct here. Don't forget what we have here is just representing this thing over here. And over here, it is very important that the z come before the x and not the other way around, because this, don't forget, represents a determinant. That is a determinant. And when you switch two columns in a determinant, that does introduce a minus sign. So the ordering with z first and x second is important. That does matter. And so likewise, analogously over here, it's important that the dz come before the dx. So don't think of this as two separate things. A dz and a dx that independently that we're multiplying together. This dz dx is shorthand representing that I specifically need the z first and the x second. And I know it's weird, but that's just what you have to do. Okay, so all together then, this is what you might call a coordinate notation for our ds vector. And if you just plug that in, and assuming that you have a vector field, let's suppose your vector field has coordinates PQR. Again, very typical. The reasonable notation that a lot of people really like is to power out that dot product like so, and thus consider this as an alternative notation for a vector surface integral. And this is what we call a coordinate surface integral. This is an alternative notation for a vector surface integral. Does everybody follow me? And by the way, note the strong analogy. We did something like that with line integrals. Here we go. We talked about coordinate line integrals as an alternative notation for vector line integrals. So, totally analogous thing here. Okay, same context. In Math219, this isn't going to buy us a thing. This won't help us compute anything. Right? I show it to you largely because it's in common use. But it's in common use because it is actually pretty awesome notation. This is actually a lot like what differential forms look like. Again, differential forms are very, very powerful tools for proving really powerful results, some of which we're seeing in this course. And so this is not a bad notation. This is a wonderful notation. It's just a wonderful notation where the wonderful does not expose itself in this class. And so in this class, I have a strong preference to stick to this. This is something that's physically and geometrically meaningful and compact and easy. And this notation here is opaque and bulky and clunky. So in Math219, I don't encourage coordinate surface integrals at all. Outside of Math219, you're going to see this whether you like it or not, and I just wanted y'all to be ready for it. Is that cool? Everybody happy? All right. Okay, symmetry theorems. Now, as y'all know, I'm a big fan. Huge fan. I think symmetry theorems are wonderful and extremely powerful. And again, I personally benefited to the tune of, what did I say, 1.8 physics classes worth of integrals, I think, if I remember correctly. It was a lot and is, totally awesome. So, as you would expect, here is a symmetry theorem. Oh, I circled too much there. Here is a symmetry theorem for scalar surface integrals. That's exactly what you would think. If your integrand is odd and if your domain is symmetric, mind you, it does have to be both of these conditions. And mind you, it's got to be the same plane for each of these conditions. But all that said, integral is equal to 0. No slicing, no parametrizing. No resulting double integral that you have to anti-differentiate, and oh my gosh, all that ugliness. Just boom, 0. Totally awesome theorem. Okay. Important point. This only works for scalar surface integrals. Only scalar surface integrals. There is no odd symmetry theorem for vector surface integrals, and the reason is totally analogous to why there's no odd symmetry theorem for vector line integrals. And it has to do with your orientation vector. Your orientation vector on two different sides of a symmetric surface, these being the little pieces in the Riemann sum that that hopefully we would want to pair up and cancel. These two normal vectors, they don't point the same direction. They don't point opposite directions. They just point different directions. And it just doesn't, odd symmetry just doesn't fit. Right? So please be careful with this. If you find yourself looking at a vector surface integral, there is no odd symmetry theorem. So please don't apply an odd symmetry theorem. That's, again, it's a crash and burn. It's there's no partial credit that I can justify in cases like that. So got to be really careful with that. Now, real quick cultural point. There is a different kind of a symmetry theorem, but it is definitely more trouble than it's worth. And I would confuse more students. I would hurt you more than I would help you if I were to tell you with the symmetry theorem that does work. It's not about oddness. It's about a different kind of symmetry. And like I say, so I'm not going to include it in the course because it's more likely to hurt you than help you. All right. So that's just a kind of a thoroughness thing. Okay, so you may have noticed as we've developed vector surface integrals that vector surface integrals and vector line integrals have some kind of common feel to them. And the purpose of this page is just to underscore all of the analogies between the various formulas involving vector line integrals and the various formulas involving vector surface integrals. So I set it up here. You'll notice that I have a kind of a line down the page here, and we have a discussion of vector line integrals over on the left and vector surface integrals over here on the right. Because of this separation and because I draw the line down the middle of the page like that, I didn't really quite have enough room to make my parameterization horizontal. Normally I like to have domain over here, target over here, and a horizontal, function arrow. I just didn't have the space, so my arrow kind of angles down, on both of these. That's just the way it had to be space-wise. So anyway, here's a parameterization of a curve, parameterization of a surface, and the various players involved. We've talked about, for example, the ds scalar representing the size of a piece of curve, and the ds scalar over here representing the size of a piece of surface. Now, one's length, one's area, they're different, sure, but they both represent size. Let's see, in each case we have what I'm going to call a derivative. The velocity is literally the derivative of the parameterization. The capital N vector, okay, well, it's a cross product of partial derivatives. I'm going to call that a derivative in the sense that derivatives are the elemental pieces that make up what capital N is. Okay, in both cases, we talk about the unit vector that points in that same direction, and in both cases, we talk about the associated, this product here. Well, let me circle that better. This product here, TDS in the linear case, in D capital S in the surface case, right? And those we represent. I'm going to represent here. There's my dx vector, and here's my ds vector. So already, the players involved here, you can see, are somewhat analogous. But now look how strong the analogy is when you write down all the algebra. Now, what we have on the page here, none of the equations that I have written down here are new. This is all old news, right? But I've got them written down in such a way as to underscore the analogies. So here we go. Let me start with, start with the derivatives. I'm just going to use the same color coding I have in the diagrams there. Those are the derivatives. Let's see the corresponding unit vectors. Let's see the scalar sizes, the DS's that is. And then let's see the vector differentials, dx in this case, and ds vector in that case. Now notice from the coloring there, the analogy is preposterously strong. It's perfect. Algebraically anyway, the structure of a vector surface integral looks just like the structure of a vector line integral. Everybody see that? That's pretty cool. This is what I like to call an eyebrow raiser. This suggests something must be going on here that we didn't anticipate. Who would have figured that a calculation based in the computation of work, a physical quantity called work, and another calculation about fluids and quantity per unit time of fluid flowing through a surface, why should there be such strong analogies between these resulting constructions? Right? This is highly suggestive that there's something going on that we don't yet understand. And let me tell you what that thing is that we don't yet understand. It is differential forms. So again, there's deep water that we're playing around in here, right? And the reason that these two constructions look so much alike is because they are both integrals of differential forms. They really are kind of the same thing. Now, this same thing that they both are is something that I can't talk about, right? So we can't dive down all the way into the deep water. But I think there's a lot of value in realizing that even if we can't see what the connection actually is, just knowing that there is a connection, aside from it being a good cultural point, right, gives you the ability to take advantage of the analogy. Right? And so, for example, some students, there's a very common way that this manifests. A lot of students find themselves trying to figure what's the deal with the capital N vector and how am I supposed to think about the capital N vector? Well, per this analogy, it's playing a role that's a lot like velocity. It's not velocity. It's different. Different details here, but it's playing an analogous role in the calculations and in the setups. Okay, so I think that's a neat observation to make, and it can be useful again in thinking things through. Just for fun, let me go ahead and continue with the color coding down here. Oh gosh, I'll try to be quick with this. Okay, hope I don't miss anything. Let's see, the green. Okay, yeah, right. So, what did I forget? Oh yeah, and then the dx and the ds. Okay, so again, notice the color coding. Perfect analogy on both sides of the line. Okay, so any form that you have for a flux integral, there is an analogous form for a vector line integral, and vice versa. So, anyway, I think this is a nice little summary page if nothing else. Okay, moving along. Real quick pause. Does anybody have any questions about any of this? Everybody's all right? Right. Okay, so, yeah, moving along. Let's talk about Stokes' theorem and Gauss's theorem. This is another one of the monster sections in the book that really ought to be at least 2 book sections in my opinion, but everybody's different. But Colley does this in several places, like the section on change of variables. My gosh, that should be at least 2, maybe 3 sections, and this one likewise should be at least 2, in my opinion. But it doesn't matter, whatever. It's just numbering. So they do Stokes' theorem first. There's a good reason to do Stokes' theorem first. But there's also a good reason to do Gauss's theorem first, and I personally prefer doing Gauss's theorem first. So we're going to start in a different order than what the book does, talking about Gauss's theorem, and here we go. Colors. Starting with Gauss's theorem. What you're going to find as we go through Gauss's theorem here is that there's a strong analogy, very strong analogy, between Gauss's theorem and Green's theorem. They have a lot of common features. I've written down these notes deliberately to underscore that analogy. So you may recall when we were doing Green's theorem, the very first thing I did is I talked about some details about how we're going to use the word boundary. And then I talked about accumulation and accumulating quantities. And then I specified a specific quantity that I claimed was an accumulating quantity, and we drew a picture and justified that it was an accumulating quantity. And then I argued that that means that this accumulating quantity behaves like stuff. It's not actually stuff, but it behaves like stuff, so we can treat it like stuff. And then computed or claimed an associated density and wrote down a theorem. Right, so you'll see we're following that same roadmap here. Strategically, it's really a very, very similar process. So anyway, I like to point that out as we go. So be thinking about the analogy with Green's theorem as we go along here. But we do need to worry about the details. They really do matter here. Let's start with boundaries. here we go. Here's a solid. That's a weird solid. Think of this as being like a cantaloupe, something like that, right? And so it's solid, except it's got a great big air gap in the middle of it. Right? Okay, so what do we mean when we say the boundary of this solid? And a lot of people would say, well, boundary means the surface, like so. But don't forget, the cantaloupe is hollow, and there's also boundary on the inside in this particular case. Not always, right? Sometimes it's solid all the way through. Okay, but for this surface, that's the boundary. But this ignores orientation. And remember, one of the big takeaways from Green's theorem is that this word boundary is now an oriented word. That word boundary implies a specific orientation. It's a loaded word. And which orientation does it mean? What is it loaded with, in other words? It's another one of these conventions. It is an arbitrary convention, but again, arbitrary and standard and therefore not optional. And here is the rule. The orientation is always away from the solid. So let's see what that means in actuality. If you look at this point on the outside boundary, if I were to go this way perpendicular to the surface, I'd be heading into the meat of the cantaloupe. And that's not away from the solid, that's toward the solid, into the solid as it were. And so away from the solid in this case would be outward. Okay, but again, tempting to say, isn't it easier to just think outward? Geometrically direct. Why do I need to say away from the solid? And the reason why, unfortunately, is that away from the solid is not always outward. If you take this point here, if I were to go what you might call outward, if I were to go like that, that's again into the meat of the cantaloupe. That is not away from the solid, that's toward the solid. Away from the cantaloupe, away from the solid would be that way, which I think most people would call inward. So be careful with this seeming simplification of calling it outward. That's just not true, right? It's not always outward. It is always away from the solid. Everybody see the distinction? Questions? Okay. All right, arbitrary, true. But again, very standard, very conventional, and not optional, therefore. All right. We've talked about accumulation before. I'm not going to repeat all that. An accumulating quantity is any quantity where the whole is the sum of the parts, right? And obvious examples of accumulating quantity are things that are physical stuff, right? Population. Right? If you have ants crawling all around some sort of a surface or what have you, the total number of ants, well, if I were to subdivide and say, let's look at these ants over here and those ants over there, the whole number of ants is the sum of this number of ants and that number of ants, right? It's just, stuff, physical stuff we think of as accumulating quantities. Sometimes there are what you might call geometrically defined things that accumulate, and boundary flux is the example here. It's a little counterintuitive, right? If I were to say surface area is not an accumulating quantity. The surface area of the whole is just this purple area, but the surface area of the left side also includes, the cut face that creates the left side, and then the surface area of the right side would also include that cut face, and then when you try to make the whole equal to the sum of the parts, there's these leftover pieces, right? So it just doesn't work. Surface area is not an accumulating quantity over volumes, but boundary flux is. So keep in mind, boundary flux is an oriented thing. Boundary flux, the understanding oriented away from the solid, like so. Casually, we can get away with saying outward, right? Now, if I look at the left piece, the boundary flux on the left piece tracks what you might call the left part of the purple boundary, but then there also is that piece, right? And then you look at the outward-oriented boundary flux for the right piece. That, again, tracks the purple. But then there's also this blue. And when you compare the purple with the green and the blue, there's a lot of cancellation. And it's tempting to say that there's leftover here, and this leftover is the reason that the whole is not the sum of the parts. But if you look carefully at that leftover are two fluxes over the same face, but with opposite orientations, so they cancel. There's actually no leftover. Everybody on board? Now, of course, you can't help but notice this is very analogous to, let's see, here we go. Very analogous to something that that we wrote down when we were talking about Green's theorem. With Green's theorem, it's an area that when you cut, you get two pieces of line integral on a shared edge, opposite orientations, and they cancel. Just like what we're seeing here, shared face, opposite orientations, and they cancel. So this is strongly analogous to our development of Green's theorem. Just, different because we're looking at a different accumulating quantity. We're looking at boundary flux, not circulation. Right? So yeah, sure, different accumulating quantity, different dimension even. We're in we're looking at three-dimensional solids now, as opposed to two-dimensional, regions in the plane. Lots of differences, but structurally extremely analogous. And I see now I'm out of time, so we're going to draw the line right there, call it a day. See y'all tomorrow, Wednesday, and have a good one.